Yes.
All right. So this is from, I think this might be from Jan 2020 or some paper. I remember that we practiced some of these papers for your school exam. And if you remember, during that time, we had to skip some questions, one or two questions, specifically the ones which were from organic chemistry, if you remember.
Yeah.
So this question has an NMR portion at the end, I think. There is a part relating to NMR here at the end. So this is a big question. We're going to practice this whole question, all right?
Yes.
Okay, so first part, you can see here, what are they asking us? They're asking us that this lactic acid is given. Now, lactic acid, the structure is given to you here, and it's a carboxylic acid, you can see here. Why is it a carboxylic acid? Because it has a C-double-H group. That's why. Okay.
All right.
So this is a carboxylic acid. So lactic acid is a kind of carboxylic acid. And this is the structure. Then the first question they're telling us is give a reason why lactic acid shows optical isomerism. Would you like to, share your thoughts on this question? Or if you would like to say anything about the answer? We know optical isomers, right? We know what is optical isomer. Remember those enantiomers? Positive
Yeah.
enantiomer, negative enantiomer. So
Yes.
could you tell me why like what could be the answer to this question? It's just 1 mark, so very simple answer actually. Any suggestions?
Um, Probably because it's a chiral carbon.
Yes, that's the answer. So the central carbon that you can see here, the central carbon has 4 different groups attached with it. Yes.
Yeah. Yeah.
So that means it's a chiral center, right?
Yes.
And not only is it a chiral center, it is a non-superimposable on its mirror image. That's the most important point. Okay. So here we are
All
going to
right.
say that um, there is a chiral center and the molecule or the compound is non superimposable on its mirror image. All right, this will be your answer for this question. Does this make
Yeah.
sense?
Yes.
Okay. And then they're telling us that a laboratory sample of lactic acid does not rotate the plane polarized monochromatic light. They said give a reason for this observation. So so they're telling me that imagine I have a sample, okay? I have a solution and
Yeah.
imagine this is filled with lactic acid. Now lactic acid, we know that it shows optical isomerism, right? So it's supposed to rotate the plane of polarization of light. It is supposed to either clockwise or anti-clockwise. It must be able to rotate it. But in this part, they're telling me that apparently there is a sample of lactic acid which is not rotating the light. Would you like to guess the answer? Any suggestions?
All right.
Why would it be that even though lactic acid itself is an optically active compound, we know that compounds which can rotate light, they are said to be optically active, right?
Yeah.
So even though lactic acid is optically active, why in this scenario, why is it not rotating the plane of polarization of light? Why could that be?
Um.
Any suggestions? Okay, so let me help you. So we know that when there's a positive, like when there's an optically active ice compound, right, which has optical isomers. Isomers are usually two types, right? One is positive enantiomer, the other one is negative enantiomer. Yes.
Yeah.
Now, what's the main difference between the enantiomers? What's the what's the what's the main characteristic difference between them?
Like difference between enantiomers?
Yes, what's the main difference in the enantiomers, or any difference that you might know?
Um, it's like enantiomers they can pass optical activity.
Yes, they have optical activity, but there is a difference in their optical activity, and what is that?
Uh,
The difference
like they
is
have
the difference is that
equal.
no, the positive enantiomer will rotate light in the clockwise direction. That is one of the difference. And the
All
negative
right.
enantiomer will always rotate light in the anti-clockwise direction. Do you remember?
Okay.
Now we have
Yeah, yeah,
discussed
yeah.
this, right? Okay,
Yes.
so don't you think that would it be possible that overall there is no effect on light? When would that be?
When like there will be like no rotation
Yes. Why will there be no rotation? Individually,
because
they can
one.
rotate. Individually, they can rotate. Right. The positive one will rotate clockwise, and negative one will rotate anti-clockwise. But in some cases, as in the case of this laboratory sample that they're talking about in the question, why is it that the plane of polarization of the light is not rotating? Why could it be?
Because one is in clockwise and other in anti-clockwise.
Sure, sure. But what are you, so exactly what are you trying to mean? Elaborate. Can you, like, just a bit more
Like
detail?
both are in opposite directions, so that's why like they can't rotate.
Yes, so your answer is kind of correct, but exactly what you have to say here, you have to say that the actual thing is lactic acid can rotate the light. But the problem with this sample was that this sample unfortunately had both the positive enantiomer and the negative enantiomer. And not only did they have both, they had both in equal concentration. That's the most important point. So
Yeah.
imagine you have a sample. Okay, imagine you have a sample in which it's filled with lactic acid. Okay, so the entire thing is filled with lactic acid. Now now imagine you have 50 molecules of the positive enantiomer and 30 molecules of the negative enantiomer. Okay, just imagine this, just for an example. So
All
do
right.
I have more of the positive enantiomer or more of the negative enantiomer? Which one do I have more? I have more of the positive enantiomer. I have 50 of the positive enantiomers. Yes.
Yeah.
So that means overall the rotation will be clockwise because the positive enantiomers are available in a greater concentration. Okay.
All right.
What if you actually had 30 positive enantiomers and 50 negative enantiomers? This time who do I have more? I have more negative enantiomers.
Negative. Yeah.
So overall the rotation will be in which direction? It will be in anti-clockwise direction.
Yes.
So the question now is, in which scenario is there no rotation at all? Not clockwise, not anti-clockwise. When is that possible? That's only possible if you have both of them in equal numbers or in equal concentration.
Yeah.
And don't we call this a racemic mixture? Remember this or not? A racemic
Yes.
mixture is a mixture that has both the positive and the negative enantiomer in equal concentration. And because of this, what happens? Light does not rotate in either clockwise or anti-clockwise. There is no rotation basically. Do you remember this or not?
Yes.
Okay, that's your answer here. And then part three, they're telling us that give the structure of the organic compound or the organic product formed when lactic acid reacts with phosphoric acid. So lactic acid reacts with phosphoric acid. Now this reaction is from AS chemistry actually. This reaction is from AS chemistry. Phosphoric acid is a reducing agent. Okay.
Yeah.
And so lactic acid, let's look at the structure of lactic acid. This is your lactic acid here. So it has a COOH group. So let me, how do I show this to you? Let me open up the, one moment. Let me just open up the AS notes. So you are present in the, if you go to the AS, like unit 1 organic notes, all right? Specifically the
Yeah.
PDF that is labeled as reaction of alkenes, all right? Reaction of alkenes. If you go to that, and if you go to page 15, if you go to page 15, you're going to find this PDF. Page 15, you're going to see this label known as hydration of alkenes, okay? Hydration
All
of
right.
alkenes. Now in this PDF, it's a bit blurry here, but but basically this is, do you see the circle part here? Circled portion here. Uh, it's it's supposed to be catalyst
Yeah.
H3PO3. Wait, let me just download this. Never mind. Just give me 1 second. Let me just download this. Give me 1 minute. Here in this PDF, go to page number 15, okay? And then you're going to be here, and let me just clarify this part. Fast. Catalyst is H3PO3, all right? H3PO3, or let me just write this with my pen. So this is phosphorus acid, all right?
All right.
So here, when you take alkenes and when you put them, when you heat them with steam, all right? So you see here, heating with steam, that is H2O in gaseous state. If you heat them in steam, what happens? They turn into alcohol. Do you see that?
Yeah.
But they said H3PO4. Wait. Oh, this is H3PO4. 1 minute. Not not H3PO3. It's H3PO4. So what happens here? Alkene turns into alcohol. Yes.
Yeah.
Alkene turns into alcohol. Now, not only can it do that, it can also react with alkanes and turn them into alkenes. So, do I have that here? Liquid. Addition. Why can't I find it here? Sorry about this. Just a moment.
Sure.
Alkanes. can't seem to find the exact reaction. I'll let you know after the class, all right? I'll just take a look at that and I'll exactly show you, like I'll send to you where is it in the notes, all right?
Sure, sure, no problem.
For now, I'll just continue with this and I'll show that to you later. So I'll just continue at the moment. So lactic acid, what was the structure of lactic acid? This was the structure of lactic acid, okay? So you have the carbon joined with hydrogen. This is joined to CH3 itself. And then over here, there's a CWH group, all right? Now, when this reacts
All
with
right,
concentrated phosphoric acid, what happens is you get an alkene group, all right? An alkene group comes here.
all right,
An alkene group comes here. So specifically, lactic acid reacts with concentrated. Oh wait, never mind. It's an alcohol. Alcohol. So in this structure, it gets dehydrated. Okay, this is an alcohol. Okay, if you notice a bit closely, this compound, it has both an OH group and a carboxylic acid group. Yes, so it's an alcohol at the same time a carboxylic acid. Okay,
yes,
so
all right,
these type of compounds, we usually name them as hydroxy carboxylic acid. Okay, so because they have OH group also and carboxylic group also, so hydroxy carboxylic acid, this is the type of compound that they are.
all right,
Carboxylic. Okay, wait, now that okay, wait, I made a mistake here. This is probably there in, so here, the compound that you can see, it's a hydroxycarboxylic acid, so it has both OH group and COH group. Yes, or did I stop sharing my screen? Sorry. Uh, yeah, you can see the question. So the compound here, it has both an OH group and a carboxylic acid group. Now, when you react it with phosphoric acid, all right, H3PO4, what happens? The alcohol group
yeah,
gets dehydrated. Dehydration occurs here. So what does dehydration
all
mean?
right,
The word dehydration? Dehydration means loss of water, right? Dehydration means loss of water. So what happens? The, this carbon has how many hydrogen? The carbon at the end. This carbon has how many hydrogen? The carbon on top.
it has one. Oh, on the
Three.
top.
Yeah, on the top. Three hydrogen, right?
Yeah, yeah,
And this carbon, it has the OH group. So what happens is the OH and one of the hydrogen from those three, they get out as water. Okay. And you are basically left with this part of the molecule. All right. So the OH is gone now. The OH is gone. Is that clear? The
yeah,
OH is gone. And so that carbon has how many hydrogens now? Two hydrogens. It had three, it now has two. The carbon which has the OH, it only has a hydrogen now, nothing else. And you have the
yeah,
COOH group at the end. Yes.
yes,
Now, this carbon and this carbon, they both have one empty bond now, right? They
yes,
both have one empty bond now. So you have a double bond forming here. That's going to be your product. So this will be your product, okay?
all right,
All right. So this is yeah, this is the product, yeah. And then part B, they say this is a reaction involving butanoic acid is shown. So you take a specific alcohol and you put this potassium dichromate. This is an oxidizing agent, right? It's an oxidizing agent.
yeah,
So this alcohol gets converted to butanoic acid, and then so there's a bunch of reactions going on. So in this part, they're saying identify X, Y, and Z. They said identify X, Y, and Z. So this is butanoic acid. So if I draw the structure of butanoic acid, it's something like this: CH3, CH2, CH2, COOH. All right. So this is your butanoic acid. So can you tell me what alcohol might give you this butanoic acid? Like if you have a specific alcohol, what alcohol would you need to convert to be oxidized to get you butanoic acid? Did you understand my question?
No, actually.
Okay. They said that there's an alcohol here, but they didn't tell us what it is. So it's unknown, right? They took that
Yeah,
alcohol and they reacted it with potassium dichromate, which is an oxidizing agent. So the alcohol was oxidized to give you what? To give you butanoic
the
acid.
alcohol was oxidized.
To give butanoic acid, this one, this thing here.
Yeah, yeah, yeah.
Yes. Now the question is, what alcohol might that be? What alcohol could that have been? That's the question. What do you think? This is from Unit 2, actually. We know this from Unit 2. Oxidation of alcohol is from Unit 2.
Yeah,
So, what alcohol might we need?
butanol.
Yeah, butanol. That's it. So the alcohol X must be butanol. Now, to be specific, if I say butanol, is it so? Butanol has what? Butane means there's four carbons, right?
Yeah.
On which carbon would the OH group be? On which carbon does the OH group have to be?
Uh,
So before you answer me, tell me, this is a carboxylic acid, right? Butanoic acid.
yeah.
What what degree alcohol gives you carboxylic acid? Primary, secondary, or tertiary?
Um, I guess tertiary.
No, tertiary alcohols cannot be oxidized. What are you saying? Remember,
So like,
tertiary alcohols cannot be oxidized. 2-degree alcohols directly give you ketone, and 1-degree alcohols will give you aldehyde, which then gives you carboxylic acid. So alcohol X
yeah,
must be a 1-degree alcohol. Is that fine? Yes or no?
yes.
So to be a 1-degree alcohol, the OH group must be joined with which carbon? Will it be either of the carbons on the middle or one of the carbons on the edge?
One of them in the edge.
Why? Why? Can you answer that? That is correct, but why?
Because they didn't say one all or two all.
No, no, no. Yeah, but you are telling me one all right. You just told me that
Yeah,
it
yeah.
has to be on carbon number one, which means on the edge, not in the middle. That is what you are telling me. What I'm asking you is why. Why did you tell me that? Why not in the middle? That's my question. Your answer is correct. I just want to know
Because
the reason.
they said it's
Yes.
butanoic acid, not butane 1-oic acid.
No, no, no. That's true. That's true. That's true. It's butanoic acid. Now this one must be butanol, and the alcohol must be what degree? 1 degree, right? It must be
Oh,
primary.
oh, yeah,
So
yeah, yeah, yeah,
so the carbon that has the OH must be joined with how many hydrogen? Two or more.
yeah,
That's why. That's why. Okay. It cannot be in the middle. So the name should not be butanol. It should be butan one all. Okay. Is that fine?
yeah.
All right. So
Yes.
so that's it. And then we have to identify what is Y. So look at this. In what is happening with Y? So you take this butanoic acid and it converted to this compound. So what does this compound look like to you? Any idea? So if I draw the full structure, okay, the compound is like this, like this, and COCl, something like this. All right. Do you know what this compound
Yeah.
actually is? It's definitely not an alcohol. It's not a ketone. It's not an aldehyde, not a carboxylic acid. What is it? What is this compound? It's
Uh,
it's an acyl chloride. It's an acyl chloride. Why is it an acyl chloride? Because this part of the molecule, right? This part of the molecule, if I draw it
yeah.
for you, does it look something like this or not?
Yes.
This COCl is the acyl group functional, acyl functional group, acyl chloride functional group. Okay, so this is acyl chloride.
All right.
So they're telling me that you have to convert a carboxylic acid into an acyl chloride. Carboxylic acid into acyl chloride. How would you do that? Any suggestions? Do you remember? Okay, so if you remember, we talked about acyl chlorides back in unit 5, or in fact back in unit 4 in if you remember, topic 15C or D, I think. Topic 15C, perhaps.
Yeah. I remember discussing alcohol.
Yeah, so to get acyl chlorides, the carboxylic acid must react with PCl5, all right? So this butanol chloride must react with PCl5. Okay? So reagent Y is
Yeah.
PCl5, which is phosphorus pentachloride. Phosphorus pentachloride. And then you have compound Z. So they're telling you that you have this acyl chloride which is reacting with this compound here, and you will get compound Z at the end. This is an amine, okay? This compound is an amine. So an
All
acyl
right.
chloride reacts with an amine. So let me see if I can find the reaction for this. We definitely did this, I suppose. Uh, oh, I found the reaction for acyl chloride.
All right.
Let me show you. Here, here. You remember this? We discussed this. Here. When you take acyl chloride and react them with water, you can get carboxylic acid. Even with PCl5, I think the bond with PCl5 is not here for some reason. I think the file got deleted. It's there in the summary. So you have the summary with you, right? The PDF summary that I've given you. I gave you specific summaries, right? For example, to study your for your test. In that reaction, it's there. So let's talk about this reaction here. So this specific reaction, this part, okay? This part.
All right.
In this part, this is your starting compound, which is the acyl chloride, okay?
All right.
And this is your amine. Acyl chloride reacts with amine, and the product will be an amide, okay? The
All right.
product that we usually get is an amide. So let me help you. So the acyl chloride that they're showing here is something like this. Cl. This reacts with the amine CH3 NH2. So I'll write it a bit something like this: NH2 CH3. So what happens here is, so the product, the compound that they've written us, they've written is something like this: CH3 NH2. So how I'm going to write it is, I'm going to just change the look of this compound. So okay, not like that. I have something like that. All right. So this is the compound. So
Yeah.
this compound only I've written it just a bit slightly differently so that it helps with the reaction. So what actually happens here? This H and this Cl, they leave. Okay, they go away.
Right.
And as they go away, the rest of the compound they join with each other. So the remaining parts they will join. C O, and then so the H from here leaves, right? This H goes away and this Cl goes away. So
Yeah.
what happens is this carbon and this nitrogen they will join. All right,
Right.
something like this. Do you, are you getting this or not?
Yeah. Yeah.
This is your product. This will be, this is your final product at the end. So in compound Z, you can actually draw this structure. Okay, I think they want,
Right.
they said identify by name or formula. So if you wanted to just do the formula, you can draw the structure, and the name of them, the name of this will be um, how do you show this? So to name this compound, it's an amide. So on the left, on the right side, there is a CH3 group only, right? There's like one carbon, and on the
Yeah.
left side, there's total how many carbons? Four. So you're going to say, name it like this: N methyl. So methyl because there's only one carbon on the right side. Okay,
All right.
only one carbon on the right side. And on the left side, how many carbons? Four. So you say butane. Okay, butane amide. Okay,
All right.
this will be the name. So this is the name, and this is the structure. Okay, this is the structure. So in this case, you can either give the name or the structure. Either one is accepted. Is this fine?
Yeah.
Obviously, you'll get a byproduct, which is the HCl, but no need to write that here because they just want the main product. So, coming to part C, they said this is a polyester. So we talked about polyester, right, a few days back. I think at the
Yeah.
end of topic 15 D, I think so, something like that. We talked about different types of polyesters. So they said give the structures of two monomers that could form this polyester. Okay. Now,
All right.
this is the repeat unit. This is a single repeat unit. Okay. This is a single repeat unit. Can you figure out the monomers that can be present here in this structure? Can you figure out which one could be the monomer? Which ones could be the monomer?
Um. I guess so. Monomer is for like one.
Yes, this is a single monomer, and this is another monomer.
Oh,
Okay,
so there are two different monomers.
two different monomers. Yes, for polyesters, usually we use two different monomers.
All
Remember we
right.
talked about diols and dicarboxylic acids.
Yeah. Yeah.
So these are the monomers here also. So this one is what, diol or dicarboxylic acid? Can you tell me which one is this one and which one is this?
Uh. Dicarboxylic acid. I guess is the second one.
Yeah, the first one is diol. So if I draw the
Yeah.
structure, all right. So let me draw the first one. Something like that. Something like that. Something H, and so on the open ended there's an O only, right?
Yeah.
Now if this is supposed to be a diol, that means I only give to have to add what? That's the only thing that I have to add is the hydrogens.
Yeah.
So this is one of your monomers, okay?
Yes.
Now the other monomer is like that part. So if this is dicarboxylic acid, what else should I add on both sides? Can you tell me? This
Like I
carbon
didn't
monoxide.
understand.
This is dicarboxylic acid, right? You told me only that second one is
Yeah,
not
yeah,
dicarb. So
yeah.
what else should be added on both sides, on both edges, to make this a dicarboxylic acid?
Hydrogen.
Just hydrogen or anything else? If I give just hydrogen, does it look like a carboxylic acid functional group or not?
No, no.
Then
I guess OH.
yes. Which now it's a carboxylic acid because this entire thing is the carboxylic acid functional group COOH.
Yeah.
All right. Are we clear
All
about
right.
this?
Yeah.
Okay. So these are your two monomers. Okay. And the part D, they said an organic compound E contains carbon, hydrogen, and oxygen. So we don't know what the compound E is. Okay. So this is unknown to us. As of yet, we don't know what it is. But they did tell us that it has carbon, hydrogen, and oxygen. Yes.
Yeah.
And so if you remember, we studied high resolution mass spectrometry a few days back. I think it was just yesterday or the day before that, perhaps. No?
Yeah.
Uh,
Probably.
do you remember we looked at mass spectrometry, like mass values that were very high, accuracy, like up to 4 decimal places, something like this? Remember?
All right.
So they said that this compound E contains 5 carbon atoms. So we know that there's 5 carbon atoms, but we don't know how many oxygen or hydrogen there are. Right. Now the question says that we have to deduce the molecular formula. Now
Yeah.
the total mass by charge is how much? They've given us 102.0678, right? 102.0678. Now if this is the total mass of the compound and there is 5 carbon atoms, that means I can already do 5 times 12 because carbon. According to this table, what is the mass of each carbon? 12, yes.
Yeah.
12, yes. All right. Additionally, with this compound has carbon, hydrogen, and oxygen. They told us. Yes or no?
Yeah.
But we know that there's 5 carbons, but do we know how many hydrogens or oxygens there are? They didn't tell us, right? They didn't really tell us. What we have to do is we have to calculate
Yeah.
it. So for example, let's say there are X number of hydrogen, okay? So that means I have to multiply X with this mass value, right? Because
Yeah.
that is the mass of each hydrogen. Do you understand my question or like what I'm saying?
Yeah. Yeah.
And there is probably what about so apart from hydrogen there's also oxygen. So let's say there is y number of oxygens. Why I'm thinking x and y is because I don't know how many oxygens there are. That is why I'm taking y multiplied by what is the mass of each oxygen. 15.9949. So 15.9949. So what I want you to do is, can you try to figure out the suitable values of x and y such that the total mass is this value? Can you try to figure that out?
Yeah.
Yes. Yeah, 5. So that means instead of x, you're taking 5.
Yeah.
And instead of y, you are taking 1.
No, it gives 81 basically.
81. So that's less than 1 or 2, right? So
Yeah.
do something. So take 2 oxygen because the gap is really big, right? So I don't think you can fill that gap with taking more oxygen. So take 2 oxygen. So instead of y, take 2 and then try.
All
And
right.
then try.
No, this is 97 still. So I can
97.
try with.
Okay. Okay. 1 minute. So if you take 3 oxygen, try with 3 oxygen.
No,
Try with
it's bigger than 102
it's way
then.
bigger. So that means let's keep it at 2 oxygen and let's try to increase the number of hydrogen now. So you took 5 hydrogen
All right.
before, right? So
Yeah.
take 7 or 8 or 9, 10, try it with that.
All right.
So keep oxygen 2 and then increase the number of hydrogen.
Well, if we take 9, it's 101.06
Okay, take one more,
instead.
take one more, take one more, take 10 then.
All
Take
right.
10.
Yeah, it's exactly 102.067.
Yes, so that means the molecular formula will be C5H10O2. Is that clear?
Yeah,
All right. So just remember this as a rule of thumb that most of the cases you will have a lot more hydrogen than oxygen. I don't really think you have ever come across an organic compound where there's more oxygen than hydrogen. That's really never the case.
yeah, yeah,
Yeah. So yeah. All right. So we got that, and then number two, they said aqueous sodium hydrogen carbonate. So sodium hydrogen carbonate. It's like I think NaHCO3 is added to a sample of E, no effervescence occurs. So this is a base, right? Sodium hydrogen carbonate, it's a base. It's a base. So they added it with E and there was no effervescence.
all right.
If you remember, this sodium hydrogen carbonate, it's a specific test for carboxylic acid. Specifically, carboxylic acids give you effervescence if you take sodium hydrogen carbonate with them. All right. So that means in this scenario, so I think you know this that um, this is what hydrogen carbonate, right?
Yeah,
Metal hydrogen carbonate. So in most of the cases, and um, acids and either metal carbonate or 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 metal hydrogen carbonate. All right, metal carbonate
yeah,
or metal hydrogen carbonate. They'll usually give you an effervescence if you react acid with either them
yeah,
or them. But in this case, we got no effervescence. That means compound E, it's an organic compound. But
yeah,
can I say that for sure it's not a carboxylic acid? Because if it were a carboxylic acid, you would have gotten effervescence.
yeah,
All right. So our conclusion can be that E is not a carboxylic acid. Is that fine?
yeah. That's fine.
Okay. And then they said the infrared spectrum of E has an absorption in the range 1750 to 1735. They said, what is the functional group? So for these type of questions, you have to refer to the data booklet. So let me open the data booklet. Again, the data booklet will be given to you in the exam. They'll give you a separate book for that when you give the exam. Let me open that 1 minute. I think the data booklet is given in the Google Classroom. So if you feel like you want to go through that, it's there. I think I uploaded it in Google Classroom. So they were talking about infrared spectroscopy, right?
Yeah,
Infrared absorption. So there is a specific section in the data booklet specific to infrared spectroscopy values. Here, you can see here.
yeah,
These are all infrared. So they said something. What were the value they were saying? They said 1750 to 1735. Okay, 750 to 1735. So now let's look at the values and try to find out what range is this, like what group or what bond gives you this absorption. 1750. So 1717. If I check 1717, here I'm getting some here. I found the exact value, 1750 to 1735. Do you see that?
yeah.
So that must be it must be an ester functional group.
Yes,
Is that clear? So here
yes.
you come back here and then you say ester. That's it. Okay.
All right.
All right. So after this, you come to part four, and this is the question why I was actually. Oh, sorry, I closed screen sharing. Yeah. So the next part, you come here, and then this is the part that I actually wanted to discuss because this is NMR. So after that, they told you that, remember, we are still discussing for compound E, right? We don't know exactly what it is. I mean, so far we have discussed that it is an ester. We know it's an ester,
Yeah,
and we know that it has the molecular formula C5H10O2, right? This is the information that we have discovered so far. Now they have given you all of this information, that is the NMR spectrum for this compound, and these are the
all right.
information. So you can see how many different signals did we get. We got 1, 2, 3, 4 signals. Yes. So since we got 4 signals, there are how many different chemical environments? There are 4 different chemical environments. Yes.
Yeah,
This is what we were discussing for the last 2 classes actually. So we have 4 different chemical environments. Now, you can see here that they're giving you some chemical shift values, right? Chemical shift values and
Yeah.
also the splitting pattern. So whether it's triplet, singlet, or whatever is going on, they've given you that. And then lastly, they've told you to deduce the structure of E. So you have to actually figure out the actual structure. So let's take these values and take the help from the data booklet. So if you go to the data booklet, again, in the data booklet also you have the NMR data information. So again, in the question, do you see that they've told you this is a proton NMR?
Yeah.
Yes. They didn't say just NMR. They told what NMR? Proton NMR. When they say proton
Yes.
NMR, that means we are targeting hydrogen atoms. Yes.
Yes.
And if you go to the data booklet, sorry, I closed it by mistake. If you go to the data booklet, you will see that there's a specific page where they've given you all the bond, all these NMR chemical shift values specific to a hydrogen atom. So now in the question, they have given us some values. For example, 4.02. So these are the values that were given in the table. 4.02, 2.05, 1.65, and 0.95. So I just written the values here so I don't have to keep going back. So let's see, 4.02. 4.02 is like here, right? Exactly here. Do you see the table? In the x-axis here, in this level label here, 4.02 is
Yeah.
somewhere here. Now at 4.02, obviously we don't have any halogens, so ignore this. We don't really have any alcohol, right? Our compound has
Yeah.
no alcohol functional group, but our compound does have ester. So this is the you know, possible spectrum.
Yeah.
Now, what does this actually say? It says that what does it actually mean? So remember, for NMR spectroscopy, for proton NMR, we are targeting hydrogen atoms. Specifically, this is what hydrogen? This is a hydrogen that is joined with a carbon, and that carbon is joined to what? Joined to another oxygen actually. All right, a hydrogen joined with a carbon that is joined with an oxygen. Does that make sense or not? Hello?
Yes, sir. Sorry, I'm having internet
Yeah,
issues.
yeah, sure,
So,
sure, no
like,
problem.
your voice was lagging.
Yeah, yeah, no problem. As long as you can understand, just
Yeah, yeah.
if it
Now
lags, no
it's
problem.
clear. It's clear.
Okay, okay. So in this table, again, what is this actually signifying, or what does this actually mean? Specifically, they're talking about a hydrogen which is joined with
Yeah.
a carbon, and
And
that
oxygen.
carbon has an oxygen on it. That is what we're dealing with here. So the peak A, all right, the peak at A, it shows a splitting pattern of what? It shows a splitting pattern of it shows a splitting pattern of triplet. Do you see that the first chemical shift? It shows triplet, yes?
Yeah.
It shows triplet. So since it's showing triplet, now let me just clarify. We know that it's an ester, right? That means it must have this portion. Whatever it has or whatever it doesn't have, it must have something like this in the middle for sure. An ester always has this, yes or no?
Yeah.
And then there's usually some parts joined on the left side, some on the right side. Now we know that our compound has how many carbons? How many carbons? Five. We know this. We already know that there are five carbons total. Is that clear or not?
Yeah.
So let's attach a carbon here and a carbon here. Now we don't know if this is correct, okay? I'm just guessing this at this point because it could be that all carbons are on the right side or all carbons are on the left side, yes?
Yeah.
However, if you remember this chemical shift 4.02, we found out that this chemical shift was due to a hydrogen which was joined with a carbon that was joined to an oxygen single bonded. Yes or no?
Yeah.
So here, which carbon is joined with an oxygen? Can you tell me single bondedly? This one, right? This
Yeah.
carbon is joined with an oxygen single bondedly. Yes or no?
Yes.
Now this can have a hydrogen. Now you could argue that it could be this carbon also, but the problem is this carbon, it can have a hydrogen, I guess. It could have a hydrogen. So it
All
could
right.
mean that there's a hydrogen here. So that's a possibility. We are not yet sure. And what was the relative peak area? Relative peak area was 2. Do you see that? Do you see the relative peak area for the signal A? For signal A, the relative peak area, how much is it? It's 2. That means how many hydrogens
Yeah.
was responsible for this peak? 2 hydrogen atoms. And that's only
Yes.
possible with this carbon, right? Because this carbon cannot have 2 hydrogens. It can only have 1 hydrogen.
Yeah.
That means this is not true, all right? We can ignore that. Is that fine?
Yes.
So this is correct. That means this is a carbon which is joined with an oxygen, and the carbon itself has 2 hydrogens. These hydrogens are responsible for the triplet peak. Yes. Why
Yeah.
triplet? Can you tell me? Why is it triplet? Because the value of n plus 1 must have been equal to 3. And
Yeah. Yeah. Because it's two. Yeah.
because what is 2? Because what is 2?
Like the relative peak area.
No, no. The relative peak area is because the hydrogens themselves are 2 hydrogen
So it's
atoms.
based
But
on the chemical environment.
yes, the value of n is the chemical environment, not themselves.
Okay.
Remember. So so we know that the value of n is 2. That means this carbon, right? The carbon that we are talking about right now,
Yeah.
this carbon, possibly it has a neighbor, and perhaps that neighbor has 2 hydrogen atoms. Can we agree or can we not agree?
Yeah. Yeah. I agree.
Okay. Okay. So that's so far we came to that conclusion. So that was 4.02. Now let's look at 2.05. All right. So let's go to the data booklet and 2.05. So 2.05 is somewhere around here.
Yeah.
2.05. So 2.05, obviously these two boxes are completely ignored because no alcohol, no halogen. But ester, do you see ester again? Again, ignore amine. We have no amine, no amide, nothing like that. Or we don't even have any ketone group. We know that, right? So we don't need to consider them. Is that clear?
Yeah.
But we do have ester, so we know that it's an ester. And what hydrogen are we looking at the moment? It's a hydrogen joined with a carbon that is joined with another carbon with a CO group. Yes.
Yeah.
All right. Remember this part, okay? Remember this structure. Just try to remember this, please. All right. So we saw that signal B, right? We're talking about signal B at the moment. Signal B was because of a hydrogen which was joined with a carbon that has a CO group. Yes.
Yeah.
Not only is the CO, that's a C double bond. Did you notice that? It was a C double bond. Where is the C double bond here in this structure? There's only
Yeah.
one C double bond, right? There's only one C double bond O. Yes.
Yes.
That means this must have a carbon which has a hydrogen. And this hydrogen was giving you the signal at 2.05. Yes or no?
Yes.
All right. Now, what is the relative peak area? What is the relative peak area? 3.
Yes.
That means how many hydrogen must have there been in this environment to give you that
Three.
signal? 3. Also, pattern. Look at the pattern. What is it? It's singlet.
Yeah.
That means the value of n plus 1 must have been 1. And value of n in that case is how much? N is 0. Why is n 0? Why is n 0?
Because
Because
there might be no like same environment, chemical environments.
not only that, there is no neighbors, no neighboring hydrogens at all. That's why.
Yeah. All
So
right. Right.
so so look at these 3 hydrogen atoms. Do they have any neighboring hydrogen or not? They don't actually, because their neighbor is this carbon, right? And this carbon
Yeah.
has no hydrogen. Is that clear?
Yes.
So it's matching. My structure is matching with the data.
Yes.
Okay. After that, we have 1.65. So let's go back to the data booklet. 1.65. 1.65 is here, all the way here. And at this value, there's only one table, which is the alkene table. So hydrogen joined with a carbon that is joined with another carbon. All right.
All right.
So this signal, signal C, we are now talking about signal C. So signal C is due to hydrogen that is joined with a carbon. The carbon is joined with another carbon. And what is the relative area? 2, right? Relative area 2. So
Yeah.
now we know that our compound has, this ester has how many carbons? How many carbons? 5. So
Yes.
we already drew how many carbons here? 4, right? So there must be another carbon on this side,
Yes.
because we cannot add another carbon on the left side, right? Because the left sided carbon must not have a neighbor. It must not have a neighbor. We agreed on that because we got a singlet, remember?
Yes.
So the neighbor must be here, and the only possible structure is this one, right? CH3.
Yes.
And if you actually match here, what was the n plus 1 value? N plus 1 was 6, which means n was how much? Sextet means 6, all right?
Yeah.
So n means n was 5, yes or no? N
Yes.
was 5. So which carbon, which hydrogens have 5 neighbors? Have 5 neighboring hydrogens. Can you figure out?
Yeah.
Which ones? Can you figure out? Which hydrogen atoms have 5 neighboring hydrogens? For example, did you understand what I'm asking you?
Uh, so like the
Hello?
that carbon has only one neighbor,
Which carbon? Which carbon? Which carbon?
like the green squared one.
Yes, that only has one neighbor, which has 2, right?
Yeah.
So that's
Yeah.
that.
Yeah.
Now we already figured it out that that's what that one gave you triplet, right? That was the triplet signal.
Yes. Yes.
That was the triplet signal. So wait,
Yeah.
was that the triplet signal? Yeah, that was the
Like
triplet signal.
two peaks.
Yeah,
Yeah.
yeah, that was a triplet signal. So it can be that one, right? It cannot be that one. What about this one or this one?
Both of them have five. Like the middle one has three neighboring hydrogen.
No, 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 no. More than three. It has two neighbors. It has one neighbor on this side, another neighbor on
Oh,
that side.
yeah.
So
So
total how
five,
many
five,
neighbors? So five.
five,
That
five.
means signal C was due to this carbon. So not the carbon specifically, this hydrogen atom, this hydrogen and that hydrogen. Yes or no?
Yeah, yeah,
And finally, you got 0.95, which is again same group. All right, this will also give you same signal 0.95. And why triplet? Because value of n plus 1 was 3, so n must have been 2.
yeah.
Do you think you can agree with this on these hydrogens? Neighbor is two carbons on two hydrogen neighboring hydrogen. Check. Look at the structure and you can easily find out that this hydrogen, this hydrogen, and this hydrogen. How many
Yeah.
neighboring hydrogens do they have? They only have one neighbor, no?
One. Yeah.
And the neighbor has how many hydrogen?
Three hydrogens.
No, I'm talking
No,
about them. So
they
who
have
is
only
their?
their neighbor have only two hydrogens.
Yes, exactly. So that neighbor is this carbon, right? This one, and that has two hydrogens. So that makes sense. N must be 2 in that case. And also look at the
Yes.
relative peak area. How much is the relative peak area?
Three.
And you can see here exactly 3 hydrogens are giving you that signal. Is it
Yeah.
making sense or not?
Yeah, it's making
So
sense.
this is your ester structure. All right.
Yeah.
So you can see here that it's not really that hard, as hard it might have seemed in when we were discussing, because in the question they'll give you more than enough information to figure out the
Yeah.
structure. All right, they'll give you a lot of information. Also, if you count out the structure, you will see that the molecular formula of this is C5H12 or H10O2 actually, because that's what we figured before, right? C5H10O2. If you count, you will see that it matches with this molecular formula. Okay, is that fine?
Yeah.
Okay, so I think that's it for this question. We won't discuss any further because I'm specifically wanting to discuss the NMR questions. So that's it for this paper. And then we'll move on to the next question. This is from, maybe, I think this is some paper from 2021 or October 2020 maybe. So this is also related to organic chemistry.
Yeah,
So yeah, read the question. I'll give you some time. Read the question and then I'll discuss. Okay, just a minute, just a minute. Um, just coming back to this structure. All right. So how many different chemical environments there are? Can you tell me? Coming back to this. Sorry about that. How many
sure,
different
sure.
chemical environments there are?
Like uh, the one carbon has three hydrogen and two has two hydrogen attached to it.
Yes, but do you think that do you do you think that these hydrogens and these hydrogens have same environment?
Like which one?
CH3, CH3 on both edges.
No, no,
No, no.
no.
So total, how many different chemical environments? So
Three different.
no, no. This is one.
Yeah.
This is two. This is three. This is four. Four different chemical environments.
Oh, sorry, sorry. My screen was zoomed in, so I couldn't like see the
Okay, okay.
very
So
far one.
that means
Yeah.
this hydrogen, and this hydrogen, they have one type of chemical environment. This hydrogen and this hydrogen, they have another type of chemical environment. This hydrogen and this hydrogen, they have the third type of chemical environment. And finally,
Yeah.
this hydrogen, this hydrogen, and this hydrogen, they have the fourth type of chemical environment. Is it clear?
Yes.
Which is why, check this table. How many different signals you're getting? Total one, two, three, four signals. I'm getting four different signals. Is that clear?
Yes.
All right, all right, all right. Yeah, we're done with that. You can go through this. Again, these are from recent papers, so you can expect these type of questions in your actual exam. All right. That A, B, C, D, and E are all carboxylic acids. Not A, B, C, D, not E. A, B, C, D. At least A, B, C, and D. They're all carboxylic acids. Yes.
Yes.
Okay. So my first conclusion from this information is A, B, C, D. What? Why now? A, B, C, D. I can be sure that they are all carboxylic acids. If they were not acids, they would not give you the carboxylic acid, carbon dioxide effervescence. Okay, that is the first information that we can understand. Then they said isomer A is straight chain. That means A is not branched. That
Yeah.
is the second information. So that means A has no branches. Okay, that is the information that they've told us. And then they said isomer B has only two peaks. Both are singlets. Okay, that means there's only two different environments. Yes,
Yeah.
two different environments. And they said isomer C has a chiral center, but isomer D does not. I think we know what this means. That means in isomer C, there is a carbon that is joined to four different groups. Yes.
Yeah.
Okay. So let's draw with A. So for A, B, C, D, we know that A, B, C, D, they're all carboxylic acids. So that means they all, and when I say all, I mean it. They all
Yeah.
have a COOH group somewhere. They all have that. So I can just draw that directly. All right. I know this for sure. So let me just draw that first. Now, remember they told us that A has no branches. If A has no branch, that means I can just keep on adding hydrogens and carbons, right? CH2. I can keep on adding because I know that there are no branches. So I have no need to do any calculations or anything. I just straight up add five carbons. That's it. Yes or no?
Yeah.
So this is the compound, right? There's three, four, three, four. Okay, I added more carbons than necessary. Sorry. That's your
Yeah.
structure. This is your carboxylic acid. We know it's straight, no branches, so I can easily draw this. Regarding B, C, and D, what extra information did they tell us? They told us that B has two peaks with
Yeah.
both are singlet. So two peaks. Now
Yeah.
two peaks and both are singlets. So let's see. Two peaks and both are singlets.
Yeah.
Uh, difficult. So I think I can do C faster because this is C is a chiral center. That means this carbon, perhaps it must have four different groups. So it must have a hydrogen. Let's give a CH3 and let's give this C2H5. Does it make sense?
Yes.
Because I know that the central carbon has to be a chiral center. This has to be a chiral center. And you can see that it's actually having four different groups at the moment. And I think that's 1, 2, 3, 4, 5. That's 5 carbons, right? So that makes sense.
Yeah.
Structure C. Structure D, they said, does not have a chiral center. But B, they're saying it has two peaks in its NMR. Two peaks. That means two peaks. So since it has two peaks, that means and they said both are singlets. So both singlets. Neighboring carbon, two peaks, both are singlets. Can you see if you agree with this structure? Can you see if you agree with this structure? Because why did I draw this? All right, let me help you understand.
Right.
Can you tell me whether you think that this hydrogen, and this hydrogen, total 9 hydrogen atoms, they have one type of environment? Do you agree with that? Don't you think that these 9 hydrogen atoms, they have the same chemical environment?
Yes, sir.
And this single hydrogen atom, this has the second type of environment.
Yeah.
What about their spinning pattern? Would you expect this to be singlet, doublet, triplet, whatever? What do you expect for this hydrogen and this hydrogen, these 9 hydrogen atoms? Talk to me about the neighbors.
Uh,
Tell me about the neighbors. What do you think?
I guess it might be a triplet or quartet.
Why? Why? Tell me about the neighbors first. For example, which one are you talking about? The 9 hydrogen atoms or the single hydrogen?
The 9 hydrogen atoms.
Okay, so they all have the same neighbor, right? They all have the same neighbor.
Yes.
And the neighbor, does the neighbor have any hydrogen?
Yeah.
No. The neighbor has no hydrogen. Take a closer look. The neighbor has no
Sorry, sir.
hydrogen.
Your voice was lagging. I'm facing internet issues. Can you repeat?
Yes, sure. So the neighbor, does the neighbor have any hydrogen?
Like it has one hydrogen.
No, the neighbor doesn't have hydrogen. Take a closer look. The one hydrogen is this hydrogen is joined to this carbon, not the central carbon.
Oh, yeah.
So don't you think n plus 1, it will be 0 plus 1?
Yeah.
So you will get singlet, yes?
Yes.
Also for this one hydrogen, what is n plus 1? If you did n plus 1, what did you do? Same thing, right? Because this one's neighbor is also this carbon only.
Yeah.
Moreover, more importantly, isn't this a hydrogen inside a OH group? Isn't this hydrogen with an OH?
Yeah.
And we talked about this that whenever hydrogen is inside a OH group, it's always singlet. Do you remember
Yeah.
this? So doesn't this make sense that both singlet? This one is also
Yes.
singlet, that one is also singlet, and how many different environments? Two different environments. These nine
Yes.
hydrogen atoms have one type of environment, and this single hydrogen has a different environment. So it matches with the information in the question. Do we agree?
Yes.
Okay. So we concluded the structure of A, B, C, and finally we have one more, which is structure D. So what else is left? What is the other possible combination for? So I mean the only possible combination I can see is something like this, something like this. I don't really see any other possible combination. What do you think? To make 5 carbons total, apart from whatever we have drawn, this is the only possible combination that I can come up with.
Yeah.
Let's see, 1, 2, 3, 4, 5. What do you think? Take a look at them and tell me if you have any confusion with any specific one of them.
Um.
Hmm?
No, no, I'm getting it.
Are you understanding?
Yes, sir.
Is it clear? Should I move on, or can I move on?
Yeah, yeah, you can.
Okay. And then they said isomer E contains an ether functional group. So we talked about A, B, C, D. All right. Now this is a different isomer, same type of compound but different isomer, and it has
All
ether
right.
functional. So ether is a compound that has something like this. Right. So it has COC. All right. This is the ether functional group. That's it.
Yeah.
So anything can be attached on two ends, but in the middle there is a COC. Okay. That's it.
All right.
And a ketone functional group. So this is the compound. All right. Of E.
All
So
right.
this is the ether portion. Ether functional. Let me use the color. So this is the ether part, and this is the ketone part. Okay.
All right.
So now they said the 4 hydrogen environments responsible for the peaks are labeled. So you see that they're making the question so much easy for you. They even labeled you the different types of environments. Are you getting it?
Yeah.
So this is A. That means these 3 hydrogens have one type of environment. This is B. That means these 2 hydrogens have another type of environment. And then C, which is for these 2 hydrogens, and D for these 3 hydrogens. Is it clear?
Yes.
So the question will help you. So you don't have to worry about NMR too much. They will give you enough clues in the question. So now you have to complete this table. Okay. So relative areas. Can you please help me finish this table? I think you know how to make the relative areas. So they even filled up one for you. So for A they gave 3. Why 3? Because relative area is dependent on how many hydrogens are there in that environment, right? For example, in environment A, how many hydrogens there are? 3. Can you see in the structure?
Yes, sir.
Inside environment A, there's 3 hydrogens, which is why the relative area is 3. What about environment B? How many hydrogens are there inside environment B?
Environment B.
How many hydrogens? Look at the structure. Take help from the diagram.
It has 2 hydrogens.
Yeah, so the relative area will be 2. What about C?
C has 2 as well.
2, and D has 3, right? Is that clear?
Yeah, yeah.
Okay. And then chemical shift. So chemical shift, let's look at this later because I have to go to the data booklet. Before looking at the chemical shift, tell me the splitting pattern. So they told you for A it's singlet. What about B? What will be the splitting pattern? So this was singlet. What will this be?
Uh,
Look at B, look at the environment B, and then look at their environment, look at their surrounding. That will help you.
I guess it will be uh double, like
Why double? Why double?
because its environment has 2 hydrogens.
So n plus 1, do n plus 1.
Oh, a triplet.
Triplet. Yes, keep on doing it for C and D. Do the same thing.
For C, I guess it will be triplet as well.
Yes, it will be triplet as
And
well.
for
And
D, it's singlet.
yes, singlet. That's it. Now, Apart from this, they want you to put the chemical shift values. So let's go to the data booklet and try to do the chemical shift. So for B and C, all right, for B and C, you can see that
Yeah.
specifically for B, um, you can see that it's joined with a carbon that is joined with an oxygen. Specifically, it has
Yeah.
ether functional group. Okay, specifically there is ether
Yeah.
functional group. So let's go to the data booklet and see where do we see that is carbon like joined with an ether. So ether, do you see here ether?
Yeah.
No, nowhere else there is ether. So for ether, the range is between here to here. So around
Yeah.
2.8. So this one is a bit less than 3. So right, can I say from 2.9 to 4? Can I say this? Like from here to here, this much, right?
Yeah.
So not even 4. Let's say 4.1. It's a bit more than 4. So like 4.10. Is that fine?
Yes.
So 2.1, 2.9 to 4.10. So here we can write 2.1 to, sorry, not 2.1, 2.9 to 4.1. Is it clear?
Yes.
Okay, environment C. Look at environment C. Specifically, the important characteristics are these hydrogen are joined with carbon, which has CO group. Yes or no?
Yes.
So let's go to the data booklet.
Yeah.
So carbon joined with CO group, ketone group, right? So again, do
Yeah.
you see ketone here? Ketone. So you see hydrogen joined with a carbon that has a CO group. Isn't this matching my structure back in that compound?
Yes.
So look at the range of values from this table from here to here. So what range can you tell me? Can you guess the range, please? Just give an approximate value. You don't have to be very exact. Just an approximate. Come on,
Yes.
tell me. Give me an approximate range.
Probably 1.5 to 2.6 or 7.
1.5 to 2.6. Yes, that's fine enough.
All right.
1.5 to 2.6. Don't you think that environment C and D will be same because these hydrogen are also joined
Yes.
with carbon that has CO group. So the same thing, all right?
Yes.
Is this clear? How we are making use of this table?
Yes.
Okay.
Yes.
And then they said in part 2, state the number of peaks in carbon 13. So now ignore the hydrogens. Now let's talk about hydrogens now. Sorry, carbons now. So they said number of peaks. So if you did carbon NMR, how many different environments would you expect if you did carbon NMR? So this means that
Uh.
means yeah, look at the carbons at the moment. So this will give you one environment. This will give you another environment. This is another environment. This is
Yeah.
another environment. This is another environment. Yes or no? Total,
Yes.
how many types of environments? Based on the carbon, not the hydrogen. Each carbon has only one type of environment, right?
Yeah.
So how many different environments can we see in this compound? Tell me from the structure. Take help from the structure.
Yeah.
How many different environments?
Sorry, sir, I didn't get you. Can you
Yes, in the
repeat?
structure that you can see here, how many different environments are there? If I do carbon NMR, that is, if I target carbon atoms instead of the hydrogen.
Yeah. There
So,
are four carbon sorry, five carbon atoms.
so how many environments?
Five.
Five, because they're all different. There is no two same environment, right? Because they're all different actually.
Yes.
So how many peaks will you get? You'll get 5 peaks if you did carbon NMR.
Yeah.
For hydrogen NMR, we actually got 1, 2, 3, 4 peaks, all right, because we had 4 different environments. But this is for carbon NMR, so targeting carbon atoms, not hydrogen. Is that clear?
Yes.
Okay. And then this is relating to the absorption spectrum. Okay, so the rest of the start question no need to do because it's not related to NMR. All right. So we'll do this. We'll
Yes.
discuss them later when we do question paper. Okay.
All right.
So that's it for NMR. I just wanted to discuss these two questions because they were directly from recent papers, plus they were related to both of them were related to NMR. That's why. So I
Yeah.
hope discussing these two questions helped with understanding NMR.
Yeah. Yeah.
Okay. So